So the problem we're going to solve, the truss problem from the book, is 4-9. And that truss looks something like this. There's a pin here at A. And then do this. And then there's a roller here at E. So these points are B, C, D, H, G, F, and it's loaded with 30, what was that, kilonewtons, 60 kilonewtons, and 30 kilonewtons. Okay, and so the goal of the problem is to find the force in every member Okay, so from what I showed you in section last week, my favorite way to do these types of problems is method of sections. I only use method of joints if I absolutely have to, and like I said also, they're equivalent, because if you do method of sections around just one joint, then that is method of joints. So the first thing to see about this truss is that it is symmetric. And I guess I should also write in the dimensions. So this is 4, 5, 5, 5, 5, 4, where 4 is the vertical dimension and 5 is sort of the horizontal dimensions. So it's symmetrically loaded. The truss itself is symmetric. So everything about this problem is going to be symmetric. So what I kind of showed you last week is that I like to not consider the reaction forces if I don't have to, because it's a lot easier to me to just sort of leave them off. They're always unknowns in the problem, and they always kind of get in your way. So you can always work your way back to them if you need them. But my first instinct, or at least what I tried first, was I tried to take this section. So we'll just try it. Sorry, my phone went into low battery mode for a second there. I'll have to record the rest of this in a bit. But we'll get through this part first. Okay, so I'm going to pick that section. Okay. So we'll see if this works out for us. So we got point C, and then down here we have point G. It's seeing that 60 kilonewton load, and then FGH. This would be FGF, FCH, FCF, FCD, and FBC. Okay, but from the symmetry of the problem, we can already tell that this load and this load would be equal, this one, and this one, this one. So all of these pairs are equal to each other. So I can just redraw that free body diagram now. C, G, F, G, H, F, G, H, FCF, FC, or actually I'm going to leave it as H. So instead of F, I'm going to use CH. And then this one will be FBC. Sort of arbitrary which one you pick, but we know that those are equal to each other, right? And then we still have that 60 kilonewton force downwards. So this one had 6 unknowns, and now that we've used the symmetry of the problem, we do only have 3 unknowns, right? So you might be thinking maybe we can solve this, but we're running into some problems where some of these forces are in coincident lines with each other. For example, if I tried to take a moment around point G, FBC and its corresponding FBC, they're always going to cancel each other out. If I try to sum the forces in H, they're always going to cancel each other out. If I try to take a moment down over here, it would be point F, the imaginary point F. These two are along the line of action, so they cancel out. These two are on the same line, so they cancel out. This one is along the line of action, so it cancels out. So we could get maybe FCH. We could probably get that one. But pretty much every other equation that you're going to try, this one and this one are going to cancel each other out, and this one are going to cancel each other out, right? So this section is not actually a good choice, and you have a frowny face. Okay, and the problem is the symmetry, right? So if I tried to pick for maybe, if I went, if you can see this, if I went all the way around and did this whole body, it would have the same problem. You have this force, this force, and it would be symmetric, and so they would end up canceling each other out in a lot of the equations that we want to use. So let's try something else. Let's try something asymmetric. So I'm going to pick this one and go right through here. There we go. So I'm going to draw the free body diagram of that now. Point B, that'd be point C, H, and G. Okay, so we got FAB, FAH, FBC, FCH, and FG, F. Okay, so at least it's not symmetric this time, right? So maybe we can get somewhere. But what you're going to see pretty quickly is, again, now we have 5 unknowns instead of 3. And since we have no symmetry this time, there's no way to reduce that down. So we're going to be stuck. So you can try taking moments around maybe point A, and these ones would go away, and then FGF would go away. But you'd end up with a relationship between FBC and FCH. You could try taking moments, I don't know, around point G. These two would be out of the line of action. You could try it over here at point F, and then you take out these two plus FAH. But if you summed all the horizontal and vertical components, you'd have a whole lot going on. Basically, we have too many unknowns, so this is an untenable section, unfortunately. Oh, and I forgot 2 forces. This still has the 30 Kn and the 60 Kn. Right? Okay, so this isn't a good section either. And I don't know, just to prove it to you that maybe this isn't the best way to do this, I'm going to try one more. I'm going to try right in here. It's kind of getting messy up on top now, but you'll see it when I draw it. All right, so this is C, H, and G. All right, so we got FAH. Is that showing up on the camera? Yes, it is. FBC. This one, because of the symmetry, is also FBC. FC. CH, it's FCF, but it's symmetric, so it's FCH also. And then FGF. Okay, so this time we got 4 unknowns because of some of our symmetry that we managed to pull in here. But again, if I'm taking moments maybe around point F here, then the FBCs are going to cancel each other out. If I try to sum the vertical components, I can get FCH. Again, all the other things are horizontal. Once again, I forget the downward forces. 30 Kn, 60 Kn. Is that everything? Yes. Point being, maybe method of sections isn't the best way to solve this problem. I mean, again, as I said, method of joints is basically equivalent to method of sections in a lot of ways, but there's no nice section like there are in some of those other problems that I showed you last week. This problem, unfortunately, what we're going to have to basically do is find the reaction forces at A and E, and then we're just going to kind of suffer through propagating them through the members all the way along until we can solve for everything. So I'll show you how to do that. Okay, so now we're going to use method of joints to solve the problem. By the way, when I did a little cut there, I realized I forgot this component here, back here. So it's actually 5 unknowns in this section because I left off FBH here. But that's just for stickler back there. All right, so I decided we're going to do method of joints, which means we need to find the reaction forces at A and E. So we're going to have to draw a free body diagram of the entire system. So let's do that. All the details for now we don't perhaps care about so much. So I'm going to kind of abstract them away. So if you remember here, at point A we had a pin, and at point E we had a roller. So the reaction forces at A, we have AX, and we have AY. And then at E, we just have EY. Okay. And then we also have our other forces. So we have the 30 Kn acting here. I did not draw this proportionately. That's okay. 60 Kn acting here, and 30 kilonewtons here. Okay. So the other thing we know about this truss is that it is symmetrical, right? We can look at all of this loading and we can sum up the forces in the x direction, and we immediately know that AX equals 0. So now it's fully symmetrical. Even though we had a pin and a roller, AX equals 0, we're happy, we're good. And the other thing about full symmetry, if you want to prove this, you can take a moment around, say, this point here in the middle, like this distance, A and E. But I'm just going to write the word symmetry, just for completeness sake. Okay, AY equals EY. And again, if you don't see that, take a moment around this point and you'll see that those are equal to each other. Finally, we can use the sum of Fy equals 0. We can invoke that. And since we know AY and EY are equal to 0, each of them ends up with half of this load. So AY equals EY equals 60 kilonewtons. All right, so now we have some nice reaction forces here. We're going to use method of joints now. So again, this is equivalent to method of sections if I just took a little section around point A. So at joint A, we have this 60 kilonewton reaction force going upward. We also have a couple of two-force members. So now I'll start filling in these labels. This is B, this is H. So AB is the only member here that can support a vertical component, because AH is horizontal. So what that means for us here is that I already know this is the orientation that a force AB has to have, right? Because if this vertical component and the vertical component of this are going to cancel each other out, this has to be pointing downward. And then since the FAB is the only thing that has a horizontal component, now when we have FAH, it has to face this way. So I already know these signs are all correct, right? Okay, so the last thing I need is this angle theta. So that's this angle here, and it's all throughout, even though it doesn't quite look it in this truss, it's all throughout here. So these are all 5, 5, 5, 5, 4, 4, 4. So the triangle we're kind of looking at is theta, 4, and 5, and this is the square root of 41. Okay, so sine theta equals the opposite over this, so 4 over root 41, or the y component, however you want to think about it. Cosine theta equals 5 over root 41. Okay, so now if I take the sum over here of this free body diagram, the force components in the y direction, we have 60 minus FAB sine theta equals 0. Okay, so FAB, if you do all the stuff to make this work out, or you plug in sine theta here, is going to be equal to 15 root 41 kilonewtons, which is about 96. Okay. All right. Now we can do the x one. So remember, for method of joints, we don't get to take any moments because we only have one relevant point here. I mean, like I said, it's equivalent to method of sections, so you kind of could. You should draw it here to point H, and you should take some moments around here, and you should say, all right, that's my section now. But as far as the moments around point A are concerned, they're all equal to 0. Okay. So f of x equals 0, we have f(a)(h) minus f(a)(b) cosine theta. We just found f(a)(b), and so, oh, that's equal to 0. So if you plug all that stuff in, you get f(a)(h) equals 75 kilonewtons. Okay, and the problem doesn't ask you to do this, but as we saw in the exam, kind of the classic question is, are these in tension or are they in compression? So remember, this is sort of the reaction force, the actual member AB. And so the sign here, the real sign, is this way and this way, right? And so this would be 96 kilonewtons, 96 kilonewtons. So AB is in compression. Okay, and then for AH, we know that this is the reaction force, so what we draw here is the opposite on the actual member. I'll just fill in the actual values. That's 75 kilonewtons, 75 kilonewtons. So AH is in tension. Cool. So now we have solved for the two things of this joint. So the question is what to do next. Well, we have a couple of options. Let me do a little squiggly. All right, one thing we could do is we can move up to joint B. You could also move down to joint H. Or we could try method of sections again and see if it works this time. And so two of these will work and one of them won't. And so we'll kind of go through why. All right, so if you look at joint B, we know this force now in AB. We don't know BH and we don't know B. Which one is that? C. We don't know BC. So remember, with method of joints, since you're not taking any moments, you can only solve for the two unknowns, or yeah, you can only solve for two unknowns around the point. So we would be able to use this one. We could go to joint B. If we go to joint H, we would now know the force in AH. We'd have this downward force of 30 kilonewtons. We would not know BH, we wouldn't know CH, and we wouldn't know HG. Right? So that would be 1, 2, 3 unknowns, I believe. Yeah, 3 unknowns, so we wouldn't be able to solve here. So we can't do joint H next. Right. So method of sections, going back to where we were before. We found AB, we found AH. I don't know if these signs are the same convention that I drew here. So we could go back to this section here. We could now solve for these three. You could take a moment around this point, and you could find FBC. And then you could get the only remaining, you'd be able to get these two now using just the vertical components. We could get FCH before, and then the only thing to be left is FGF, and so we could solve for that too. And then we just have to go back and solve for BC, CH, HG later. So we could do that if we wanted to. Some of these other sections still might not work, but we've now found AB and AH, so we could do that. But since we're in already with the method of joints, I'm just going to keep moving on to the joints. So the next joint I'm going to go up here. We're going to do point B. All right, so just have to wait for a moment to work out the next part of the problem. But we're back. So just to review where we were, we're going to go to joint B next, and we're going to use the method of joints. I'm going to move it over here now, so you can see the previous work. Okay, so joint B. All right, so at joint B, we have our previous force, this is force AB. I'm just gonna write it in though, as 15 root 41 kilonewtons, which is about 96. All right, and then that is acting at an angle theta from the point. We also have, all right, so this force is going upward in this direction. We're going to have now this member, BH, which is vertical, and this member, BC, which is horizontal. So BC has to react to all of the horizontal force from AB. So we know that that force is going to go this direction. And then BH is going to react to all of the vertical force. So that will go in this direction. Okay, so we already have some intuition about what answers we expect we're going to get. So now if I take the sum of the x components, that's equal to 0 because of equilibrium. And that's equal to minus FBC plus 15 root 41 cosine theta. So project this up to here. And so remember from our previous thing, cosine theta is 5 over root 41, so this will be 75. So FBC equals 75 kilonewtons. And then again, if we want to figure out if this is tension or compression now, we can quickly draw the little BC. We can see that this force was going this way, so that has to go inward, and it's positive, so it's compression. Okay, so now for FBH, f of y equals 0, the sum of f of y, equals minus FBH plus the y component of this force. So 15 root 41 sine theta, which is 4 over root 41. So BH equals 60 kilonewtons. And then similarly, if this is, or where is it? B and H, this is how I've drawn this force at point B. So the actual reaction force on BH goes this way. So this is in tension. All right, so we've solved joint B. And now the question is where to go for the next step. Point C has some issues because even though we know it's symmetric, but again, this kind of stuff is going to be canceling. We have BC now, so we know the force on this side. We could solve CH manually. There's more things to consider here. Basically, I'm going to move down to point H next. Right, that kind of evades all of the symmetry considerations that are happening once you get over to this line. And we love evasion. If you're still here, thank you for bearing with me. I hope this has been fun. All right, so point H. We solved for FBH at 60 kilonewtons. It'll be this direction as the reaction force. Back before we solved for AB, or AH rather, sorry, AH. And that will be 75 kilonewtons in this direction. We also have the force acting downward directly on H, so 30 kilonewtons. And then we have, okay, FCH is coming in here. This is the angle theta again. And finally, okay, so I have drawn it this way because, so this is an upward force of 60, a downward force of 30, so the net force is going to be upward. So this one is the only force I can sustain a vertical component, so I'm drawing it downward. And we also have FGH. I just drew it to the right because I don't know what FCH is yet, so I can't necessarily guess. Depending on the magnitude of FCH, it'll be either positive or negative, but we're just gonna have to figure that one out later. So for now, I've drawn it to the right. Okay, so let's do the y components first, because we need to solve for FCH before we can do FGH. So F sum of Fy is equal to 0. So now we have minus FCH equals minus FCH sine theta plus the 60 upward minus the 30 downward force. Okay, so sine theta is 4 over root 41. So FCH is going to end up being 30 times root 41 over 4, which is going to be 15 root 41 over 2. Is that right? It should be half of this one. So yeah, 15 root 41 over 2 is about 48 kilonewtons. Okay, and we know the sign is right on that one. And then, so that will be, draw my little diagram here, HC. That'll be an inward force, inward, because it looks like this is the reaction here. So that will be in compression. Okay, so now we have FCH here. We can find FGH using the sum of the X components. Minus the 75 from FAH minus 15 root 41 over 2 cosine theta thanks to FCH plus our unknown FGH. And when I multiply out, the root 41s kind of cancel each other, so this ends up being 15 times 5 over 2, so 75 over 2. And FGH equals 112.5 kilonewtons. So we did pick the correct direction for FGH. Great. And this one will be in tension. All right, so we've solved AB, we've solved AH, BC, CH, and HG. The only thing left is to solve for CG. And then we use the, by the symmetry of the truss and the loading, all of these corresponding pairs are equal to each other. So all that's left is CG. So we're going to do it at joint G. We could have actually done this one right from the start just because of how it works out. So we know FCG here. It has to resist this downward force of 60 kilonewtons acting directly on point G. And then it's got that 112.5 going on from FGH. And then on the other side, since GH and G, whatever this point is, F, because of the symmetry, that's also 112.5. So it's easy to see if we sum up the y components, equals FCG minus 60, FCG directly equals 60 kilonewtons. So all that force gets vertically transferred. Okay, oh yeah, one more thing. That is in this way, it's in tension. CG. All right, so we've now solved for every force in the truss. I'm just going to draw one more big free body diagram-esque thing. I'm not going to worry about it being so beautiful this time. Maybe I should have, though. Oh well. Okay, so we found that AB was in compression. H was in tension. So then we went to joint B, and we found that BC was in compression. And we found that BH was in tension. Let's see. Right, so we went to joint H. We found that CH was in compression. And GH is in tension. And then finally this one, CG was also in tension. And then everything else is symmetric. So if you just kind of, this doesn't always work if you have more complex members like on the test, because I saw some people trying to reason out tension and compression doing little diagrams this way. But Oh, and then I kind of forgot, we would also have our good old other forces, you know. If it were a free body diagram, we'd have all those anyway. But you can sort of see, we've done it by method of joints. We've sketched out how, for example, this member being in tension, so that it like pulls downward on joint B up here, means that then this member has to be in compression. Oh. Sorry, got the low battery warning again. This member needs to be in compression to counteract that, and then this one also needs to be in compression to counteract then the horizontal components of this one. So you can sort of see how the tension down here all along ends up leading to compression kind of in these more upper members. And that's the problem. We've solved the full truss. So I don't want to do this again because it took a long time, but I will do a couple of method of sections problems just to show how it can make complex things a lot easier. Because what we didn't necessarily like here, and what a lot of people tried to do on the midterm, was we had to find these reaction forces and kind of propagate through. And maybe there was a way around that, but it seemed like it was the easiest way to do this problem, unfortunately. In a lot of cases, if you don't have to deal with these reaction forces, since they're always unknowns, we don't want to. We want to just cut right through the body to figure out the properties of the member that we care about. So that's what method of sections is for. And so I'll do a couple of problems just like I did in section last week to show how to do that. Cool. Okay, so here's the first of the two method of sections problems I'm going to do. So this problem is a truss loaded with a force of 2.4 kilonewtons here at point B and a force of 3.2 kilonewtons here at point C. And we want to find the force in this member AE. So we want to pick with method of sections a good way to do this. And what that lets us do is eliminate the reaction forces at A and F from things we have to consider. So maybe you can pause this video for a second and try to guess for yourself where we're going to make the cut. Okay, so we want to cut AE, and we don't want to include those reaction forces, so maybe the best way to do it, we're just going to go around here. Right, so that'll be our section. So we're going to draw the free body diagram of that section. So, let's see, we got this member BE with a 2.4 kilonewton force acting on it, and then it goes to C. So it's B, 3.2 kilonewtons acting at C. This is point E, this is point D. Okay. So what we end up with are three reaction forces from the three two-force members that we cut. So we have here FAB, FAE, which is the one that we want. I'll circle it in red. And then FFE. We know this is 1 meter. And this is 2 meters. Currently, we don't know the length of this member BE. Okay, so we either need to sum the components of the forces and set those equal to 0, or we need to find a point to take a moment and set that equal to 0. So which one do you think we should do? Okay, so in this case, I'm going to try to take a moment, because if I do sum the forces, this one here, FE, has some both vertical and horizontal components, so I'm going to have to take a moment no matter what, because AB is along the horizontal direction. So if I want to isolate AE, which also has vertical components, I'm going to need to take a moment. So can you see the best point to take a moment here? Ideally, we'd eliminate FAB and FFE. Right. So if you see it, it's actually not on the body at all. It's way out here. Yes. And so by similar triangles, you can see this is 2 and this is 4 right here, and then this is 1. So we go from 2 to 1, that's halfway up the similar triangle, and then from 1 to 0, that's another halfway. So I'm just going to extend this out too, just a second, just so you can see it all. Okay. So this is point A, and this is point F, and this is the point we're going to take the moment around, which I guess we can give it a name, we can call it G. Okay, and so this is 2 meters, this is 1 meter, and this here, this is 2 meters. So this is 4, this is also going to have to be 4 meters. All right, so we have some of the geometry of our problem figured out now. We still need to find the length of this member here. So if we're looking at the similar triangles again, this is 4 and this is 1, so this is 6. So this is 1.5 meters. Okay, so now we found the length of this member. So what we're going to have to do here, when we take the moment around point G, FAB is going to be eliminated, FFE is going to be eliminated because their lines of action both pass through point G. But FAE will contribute both vertical and horizontal components. So now we need to find this, how did I mark you that? This angle here. So just to redraw this triangle that we're specifically looking at, this is the direction that FAE is traversing. And we know that, well, I wrote it this way, but it'll have to do. Right, this is theta. This is our 1.5, so 1.5 meters. And then this is this 2 meters right here, 2. So tangent of theta equals 1.5 over 2, which gives us, I did this in the calculator already, theta equals 36.9 degrees. Okay, so we can get our components of FAE equals FAE, let's see, this already is facing in this direction. Cosine of 36.9. If I have an xy coordinate system this way, that'll be negative I hat plus sine 36.9 j hat. Yeah, okay. So now we have our components of this course. All right, so now we just take a moment around point G. All right, so sum of the moments around G with that a vector equals 0 equals, so we have 4 and then 3.2, and that goes out of the plane. So 4 times 3.2, that's our first component of the force, or of the moment. Okay, and then 6 times the 2.4, so 6 meters times 2.4 kilonewtons, plus the direction here, again, that'll be 6, and then the y component of FAE. So, let's see. And that'll be negative, the sign that'll be negative because the y component, as I've defined it here, is positive. So minus 6 sine 36.9 times FAE, and then for the cosine we want this length, the 1.5, and then so 1.5, the way we defined it, the force that would be this way, so that'll be negative also, minus 1.5 FAE cosine 36.9. So that's all equal to 0. Put my little k hat here, so it's a vector. All right, and then you can just solve for FAE. We'll just pretend we've already done that. 5.67 kilonewtons. All right, so now we found our force. And just looking at this free body diagram, is it in tension or in compression? Right, so this is A, this is E, and we've drawn it like this with the FAE, it's inward here, so it'd be outward here. So it's in tension. All right. So here's our next method of sections problem, and the last problem I'm going to work through for this. So we have here a truss which has a pin reaction at A, and then a roller, this is a rotor rather, a rotor at N. And it's loaded way out here at I with an 8 kilonewton downward force. And the other feature about this truss is that it sort of reduces in size as you go out here. This is a problem 4.33 in the book. So with the forces we want to find the force in member DE and the force in member DL. So again, consider this, and what do you think would be a good cut to make here? Okay, so your first instinct might be, let's cut through here and here at the same time, because these are the two members that we want. But then to do that, we'd also have to cut through CL and LM. And so we would end up with 4 different unknowns, and none of them happen to really coincide with their lines of action just because of what's going on here with it. So it wouldn't really work if we tried to solve the problem that way. So instead we need to isolate one of these and then try to use that one component to solve the other one. So which one do you think we should do first? Should we do DE or should we do DL? Okay, yeah, I'm gonna go for DE first, and the reason why is because then we have this joint at D, and since DE is horizontal and DC is vertical, once we have DE, it'll be easy to pull out DL just using this joint and then the horizontal components of DE and DL. Okay, so we are going to make a cut here through DE, and we're going to go through EL and LK. So all the way around over here to make the loop. All right, so we'll draw that free body diagram now. So we can leave out a lot of these details because they're not actually relevant to the problem. We have point E, and then it sort of comes out to this point H. And then we have a key point Ln, even though the members aren't connected to it anymore. And then we have point K here, and this ... is all the way out here to I. Okay. So, and then I need to add in my reaction forces. All right. So we have FD, which I will do this way. We have FEL. Here at point K, we have FLK. I need to throw in my 8 kilonewton force that I had originally. And then I will label this here the lengths. This is my 6 meter length. This is still 1 meter. This is still half a meter from point I to point L. Okay. So what would be a good point now if we were trying to do, we can either choose to sum components of our force or to sum a moment. So which one do you think we should choose? Right, so in this case, FLK is not quite horizontal, so it's going to contribute to both of the components, so we can't isolate our forces that way. There's FEL and FDE, one of them is vertical and one is horizontal. But just as this is slightly offset, we can't use that. So we do want to take a moment to try to solve this. And we want to eliminate these two forces that are unknowns and leave in our 8 kilonewton one. So the best point is here at point L. We're going to take a moment around L. So sum of the moments around L equals. Okay. So what do we got? We know from over here that this distance, EL, is 2 meters. So we have that R cross this F, FDE. So 2 times FDE. That'll be positive. and then we need to find the contribution of this 8 kilonewton one, but that's just 6 meters as we have here. So minus 6 meters times 8 kilonewtons equals 0. So FDE equals 24 kilonewtons. That's pretty easy, right? Yep, and then so based on this is how this is drawn, is that in tension or compression? Right, it's in tension. So D, E, FDE, FDE, tension. All right, one more to go. DE, and now we need DL. So again, I'm going to use now, call it method of joints, or you could call it method of sections like this. Joint D. Okay. So there's FDC. There's FDL. Let me make sure. Or D. Oh, I mislabeled this. Oh, potato. FDL. Sorry. DL. And then this one needs to go this way. All right. So that could be a free body diagram. I'm actually going to swap the sign here because the same arguments I was making earlier, FDE is going this way. The force, we know that it's going this way because it's in tension. And so this force here has to be going upward and to the left. So instead of this one, we're going to do FDC, FDL, FDE, which equals 24 kilonewtons. All right, almost there. So looking at this is 2 and this is 2, so this is a 4590 triangle that we have going on here. So this, we can just sum the x components. Sum of f of x equals 0. Oh, I forgot my z or k hat. Well, it's a vector now. All right, sum of f of x equals 0 equals 24 kilonewtons minus FDL, and I'll just do cosine 45, although it could be either one. And so FDL equals 33.9 kilonewtons. And is it in compression or tension? You probably already got it. DL, DL. The way I drew it here, remember it's this one rather, this one. This way is positive. FDL. So it is in compression. All right. Sorry, that was a little bit off. Hope that wasn't distracting. So we've now solved the problem with method of joints doing the entire system. We've done a couple of method of sections ones. Hopefully that's enough to get you through your homework for the week. And then I'll be back next week, and I'll see you then. Thanks.